a spreadsheet. There it is. We're going to call this T and P. There's no point changing the variables up there because that's the variables we're using, right? And in here, the key thing was 0 here and 5 because these are the years since 1970. Now, you can put 1970. The calculator takes care of the graphing, but I always like to have the idea, my first data point, I'll have as the initial population, T equals 0. And that fits in with all your science experiments. The initial temperature, when I started the stopwatch in, T equals 0. So the initial population I've got in 1970 is so-so, okay? So I'm just going to put the first 3 in. So I'm just going to grab this back here, grab this here, 0.24, 0.55, 1, 1.4. 0.24, 0. I'm just making this up. Okay, brilliant. Now, there's going to be a lot more than that. And I don't even know if I've got the right numbers there, but you have the time and the data there. From here now, we are going to do 2 things. 1, doc, insert, and it looks like a graph. But no, we're plotting the data. So it's a data and statistics. Hover, click, T. Hover, click, P. Beautiful. It looks quite linear there, but we know when we have the full data set, it's curvy. Now, before I get to the model fitting, let's just think about this sensibly. If this is exponential growth, it means the population is growing by a certain percentage each year. It's a percentage growth, it's multiplier. That's the nature of the exponential model, okay? So from here, menu, analyze, regression. And the regression menu opens up many models. And one of the models we love here is exponential. Boom. Let's unpack this. If we feed in x equals 0, let's just work it through mathematically. 1.125 to the power of 0, 1. So y is 0.27. This is the population at year 0 according to the model. It's not the exact population, but the model tells us the population at time equals 0 is the 0.2711. Okay, this is in fact the A value in your model. Here's the B value, 1.125. Now let's think about this. The X here is T, time in years. T is 1, T is 2, T is 3. If you times something by 1.125, it's getting bigger. This is the multiplier. Tell the person next to you, what is the percentage growth rate for Dubai each year, according to this? And the answer in 3, 2, 1, 12.5. 1.125 is actually 112.5%. We have 112.5% more people, okay? That's an extra 12.5%. All right, the 100% is all of them plus the extra bit. Beautiful. But you can see, can't you, that the model sort of fits the data points quite well. An extra bonus just for you, because I like this class a lot, far better than my other classes. Under here, menu, plot properties, I think down here. Oh no, my bad. I think under analyze. Okay, so my bad. Menu, analyze. Can you see these residuals? Show residual plot. Now this is quite beautiful because this residual plot shows you how far away your actual data point is from the model line. Okay, just interesting. You don't need to include this. But residuals tell you how far away is your real data from the value predicted by the model. Okay, so let's just, I don't know how to turn that off now. It's brand new to me. I just found it out last week. Yeah, maybe. So menu, analyze, residuals, hide residual plot. Bang, beautiful. Okay, it looks like the model is a good fit to the data. But then there's this magical R squared value. Okay, you don't know much about it, but R squared goes from 0 to 1. It's like a correlation coefficient for those who know it, but it only exists as a positive number, 0 to 1. If all of those points were on that line, r squared would be 1. Okay? If those points were so far scattered, r squared would be very close to 0, as in no fit for the model. Let's find the r squared value. We can only get that by going back to the spreadsheet. And this is the bit I don't think many people know. Click in the first free space after your data. We're going to go and do that regression model again, but in this window. So menu, statistics, and statistical calculation. And within this menu, can you see exponential regression is there again? And of course, when we do it this way, the X list was the time, and the Y list, I think, was the P. Okay. And now look, we've still got the same values for the A and B here, right? That looks like the same values. Yep, same values for the model. But if we scroll down, we've got the r squared value now. Here, look. And again, the closer to 1, the better the model fits the data. This is r squared is 0.966. It's a good fit. That's all we really need from the r squared value for now. Now, should we try and fit a different model for the data, one way of judging which is the better model might be what? Yep, which is the higher r squared value. That would tell you that one model fits the data better than another. But let's be careful here. Just because a model fits the current data well, it might not be a good predictor for future growth. So those are the two important points about modeling. We can always get a really good model for current data, always. Mathematicians excel at doing that. We love it. But how reliable is that model for predicting beyond the current data? Well, obviously, if you could build accurate models, we'd probably solve all the world's problems, wouldn't we? But even then, we'd still need the actual power to act. Questions?
Are there like general boundaries into like what is a good?
Yeah, I think you could. It depends. Okay, so an r squared value of 0.966 for this data, it feels quite good. But if we were in the world of medical data modeling, we might need it to be higher, because this might be a life and death situation in terms of the quantity of a drug administered to someone. Okay, so different r squared values mean different things in different situations. All we're doing at the moment is, all we can do is compare an r squared value for this model, for this data, about population growth, using the same data, a different model, we can compare the two. That's all we can do for now. Is that okay for now? Just gives you a little feel for those, getting the modeling in there, okay? So keep going. My goal for you guys is that when you type on here, I've clicked on this video because this is what I want you to do. Some of you are drawing by hand. Oh, I love that. I always put my ads on.
Let's say I was typing.
I need you to be using equation editor to type up your work now as well, okay?
Trapezoid is. So now I want to put my formula. So I'll go to insert and equation. And it starts with A equals, and then there's a fraction part. So this is where there's templates in here. So if I click on this one, and actually you'll see, so the very first one is a fraction. So, and it goes H, and then I type bracket, and it goes A.
Okay, so I've put the link to this video actually on the original modeling thing here. So you might want to go back and just open up that video. If you've never used equation editor before in Google Documents, now's the time to start learning. Be useful across your other subjects as well. You know, to write mathematically, you can't just use handwritten and take a picture and drop it in, okay? All right, guys, enough. Get back with it. I'll stop the video.